Okay, we start today's lecture. In the last lecture, we talked about the convergence theorem of Martingale. So there are three different cases. Suppose X is a martingale, and if it is bounded in L1, then we have almost sure convergence. And if it is bounded in LP for P strictly greater than 1, then we have convergence in LP. But in the second case, it is different for P strictly greater than 1 or equals 1. So it gives us the third case. So if we want to have a convergence in L1, the equivalent condition is the martingale is uniformly integrable. So if it is UI, then we have convergence in L1. Once we have convergence in LP or convergence in L1, then we know that the limit random variable x infinity has the same expectation as the constant for the sequence. Okay, so this is what we did in the last lecture, and today we will give applications to the convergence theorem of Martingale. So today we will discuss two examples. One is called Galton-Watson tree, and another called backward martingale. And in the next lecture, we talk about two other examples. So Galton-Watson tree, we start with what is a tree? A tree is a connected graph with no cycles, and the rooted tree has a distinguished vertex. We call it is the root. The depth of a vertex is the graph distance from this vertex to the root. So in fact, it is consistent with, if this is the root, this is the first generation, second generation, and third generation. So the depth of a vertex is just the number of which generation it is in. And a leaf is a vertex that has only degree 1. So this corresponds to these endpoints. They are the leaves. And now we consider a regular rooted tree. So a regular rooted tree means each vertex has a fixed number of children. So for example, here is a binary tree. This is the root, and each particle has 2 children. So this is a regular rooted tree. And if we denote Zn as the number of vertices in nth generation, so consider a regular rooted tree. Then we know that each particle has m children. Then if we denote Zn as the number of particles in nth generation, then we know that Zn equals m to the power n. So this is for regular tree. And so this is for a regular tree. But in the real life, we can imagine that the trees we encounter is a random tree. So at each vertex, it will give a random number of children at each particle. So this gives us, in order to treat a real life question, we need to introduce the random tree. So each particle will give a random number of children. The simplest model is called the Galton-Watson tree. So a Galton-Watson tree is just a tree starts one ancestor. And for this ancestor, it produces a certain number of children according to some measure mu. So this is a random number, and the law of this number is given by mu. So Galton-Watson tree. So we first fix some random distribution mu. We have one initial ancestor. This ancestor has a random number of children, and the number is sampled according to this mu. So then the new particles form the first generation. And for the particles in the first generation, each new particle will have a random number of children, and they also sampled according to this measure mu, and they're independent from each particle to one particle to another particle. And then the system just regenerates the same rule. So once a new particle is born, and then for the next generation, he just gave a random number of children, and this random number is somehow according to mu, and all these random numbers are IID with respect to each other. And then we denote Zn as the number of the children in nth generation. So for example, this gives us a Galton-Watson tree. We have one ancestor, and in the first generation, it has 2 children. And then for this guy, it has only 1 child. But for this guy, it may have 3 with some probability. Okay, so this is a random tree. We observe that if for some generation n, there is no particle at all for this generation, then there is no hope to have future generations. So once Zn equals 0, then for m greater than n, the number is always 0. So then, in this case, we say that this tree dies out. So suppose this is a model to treat a family name. So we have one ancestor and it has a family name. So we just remember how many sons he has. So this remembers how many people with the same family name at each generation. So our question is whether this family name will die out or it will survive for a long time. So the question is, whether the tree will die out or not. So whether or not Zn equals 0 eventually. And we define this probability as the extinction probability Q. So here in this model, we can imagine that for this random measure mu, if we have high probability to have many children at each step, of course, we will have high chance to survive. Then this extinction probability will be small. But if for this measure mu, we have high probability to have no children or only one child, then finally, of course, the family will die out. So the rough idea is, if this measure mu will give us more children, then we are likely to survive. But if this measure mu has a small number of children, then we are likely to extinct. So this is the question. And in fact, this question can be explicitly answered by property from this random distribution mu. So before we answer this question, we introduce several notations. So for this random measure mu, we know that it gives us the law of the number of children for each particle. So we denote pk for the probability that we have k children. Then, since this is a probability measure, we know that the summation of all pk equals 1. And then we define the mean of this measure. It's defined as m. So this is the mean of this measure. So here we can guess that if this mean is big, then we have high probability to survive. But if this mean is small, then we are likely to die. So finally, in fact, the answer is when this mean is strictly greater than 1, then there is a positive chance to survive. But if this mean is less than 1, then we will die out almost surely. Okay, so this is the mean. And the important assumption throughout this example is the probability to have 0 child or only 1 child is strictly less than 1. So because if we know that it has either 0 or only 1 child, then we will die very quickly. So we restrict, so throughout this model, we restrict that P0 plus P1 is strictly less than 1. And then our extinction probability Q is defined as Cn equals 0 eventually. So here, what do we mean by Zn equals 0 eventually? So in fact, it means that we are calculating the union of all events that Zn equals 0. So this is the meaning for Zn equals 0 eventually. And here we can also see that because if Zn equals 0, it implies Zn plus 1 equals 0. So in fact, in this union, this is an increasing sequence of events. So this tells us, in fact, this probability Q is the limit of the probability that Zn equals 0. Okay, so this is the extinction probability. And the last quantity we introduce is the generating function of mu. So f is the generating function it is defined in the following way. So for s in 0 and 1, we define f as to be the expectation of s to this random variable z1. Or if we want to write out explicitly, it is p0 plus so this is the generating function of this measure mu. So for the first a few terms of this expression is p0 as p1 and a square p2. This is the generating function. And now let us see how to use information from generating function to get the information we usually considered. So first of all, when s equals 0, we equal p0. So p0 means this particle has no child at all. And when s equals 1, then it's just a summation of all possibilities, so it equals 1. And then let us check what's the derivative of this f. So the derivative, by definition, this is the derivative of this function. And then we set s equals 1. So here we see that when s equals 1, the right-hand side is exactly the mean of this measure. So the derivative of this function at 1 equals the mean of the measure mu. And here we also see that since we assume p0 plus p1 is strictly less than 1, so this means that p2, so for the future probability, it is strictly positive. So this tells us when s is strictly positive, then this derivative is strictly positive. So we also know that for s between 0 and 1, the derivative is strictly positive. So f is strictly increasing. Okay, so this is the derivative of f. And then we take the second derivative. Okay, this is the second derivative. And here we see that since p2 plus p3, this is strictly positive, we can also see that the second derivative is strictly positive. And this tells us the function f is strictly convex. Okay, so this is the property of generating function. Is there any question? And then we can answer the question we asked before. So the question is, we want to calculate what is the extinction probability. And the conclusion is the extinction probability Q is the smallest root of fs equals s. So it is the smallest fixed point of s. So for any s, if fs equals s, we call this as a fixed point of the function. So this theorem tells us, in fact, this extinction probability Q is the smallest fixed point of this function, of the generating function f. And this is the first step. And the second step, we give us precise criteria to check Q is strictly less than 1 or equals 1. So when the mean is less than 1, Q equals 1, so we are almost surely die out. The tree almost surely dies out. And if the mean is strictly greater than 1, then this Q is strictly less than 1. So we have strictly positive chance to survive. Okay, and this is the second part. So the first part, this extinction probability Q is the smallest root of the smallest fixed point. And then we also know that if the mean is less than 1, Q equals 1. And if the mean is strictly greater than 1, Q is strictly less than 1. So this also tells us if the derivative of the function at 1 is less than 1, then the smallest fixed point is 1. But when the derivative at 1 is strictly greater than 1, then the smallest fixed point is strictly less than 1. Okay, so this is the theorem. So how to prove the theorem? So first, we will give a precise mass description of this model. So by the definition of Galton-Watson tree, what we have is we start from one ancestor, so Z0 equals 1. And then this ancestor has Z1 children. And this Z1 children give us the first generation. And then given Z1, we know that each particle has a random number of children, and the law is assembled according to mu. So we know that for each particle in the first generation, each one of them has a random number of children, and they are IID. And all these children give us the second generation. So we know that for the second generation, the total number of particles is the summation of these numbers. Okay, so this is the second generation. And generally, we know that, so suppose we know what is Zn. Suppose we know how many particles we have in nth generation. Then for the n+1 generation, we know that for each particle in nth generation, it has a random number of children. And the total number of n+1 generation is the summation of all these random variables. Okay, this is a mass description of our model, Galton-Watson tree. Okay, then let us check. So this is the mass description of the model. So first, let us check what's the mean of the number in each generation. So what's the expectation of Zn? So for a regular tree, we know that the number Zn equals m to the power n. And in fact, this is also true for the random tree, for the Galton-Watson tree. Okay, so we prove this by induction on n. So when n equals 0, z0 equals 1, and this is true. And suppose this is true for n equals k. And then let us check what happens to the k plus 1 generation. Zk plus 1. So we know that given zk plus 1 is the summation of zk random variable. And their IID have the same law as mu. So now we can see that the conditional expectation of zk plus 1, given the information of zk, it's just m times zk. Because each of them has the mean m, and they are IID, and they are also independent with zk. Okay, so then we take expectation twice. So here we see that the expectation of zk plus 1 equals m times the expectation of zk. And by induction hypothesis, we know that the expectation of zk is m to the power k. So the expectation of zk plus 1 is m to the power k plus 1. So this is, first, we calculate the expectation of the particles in each generation. And next, we want to calculate what's the generating function of Zn. So this S is a number, fixed number in 0 and 1. And we want to calculate, this is the generating function of Zn. So we want to calculate what is the generation function of Zn. And we will prove by induction that this generation of Zn equals Fns. And here Fn is the nth-fold composition of F. Okay, so first, when n equals 1, we know that Z1 just has the law of mu. And the generating function for mu is just Fs. So this is true for n equals 1. And suppose the conclusion holds for n equals k. And then let us check what happens to k plus 1. So S, Z, k plus 1. And we know that given the information of zk, zk plus 1 is the summation of random variables. So we write this summation to the product in front, in the lower. Okay, so this is S to the power zk plus 1. And now we take conditional expectation. So given the information of zk, then we know what is the conditional expectation, because this random variable, they are independent of zk and they are independent of each other. So this is product zk. And now we can take expectation of each guy. And for each one, we know that this zkj has the law of mu. So when take expectation of this one, this just give us Fs. So this tells us the conditional expectation of S to the power zk plus 1 equals Fs to the power zk. Okay, and then we take expectation twice. And by induction hypothesis, we know that the generating of zk is fk. So now its generating function of zk is fk, and now we are taking value of fs. So this is the k plus 1 composition of f. So this proves the conclusion. So So now we know what is the expectation of Zn, and we also know what is the generating function of Zn. And then let us go back to the question about extinction probability. So what's the relation between the extinction probability and this sequence? We know that Q is the probability, it's the limit of probability that Zn equals 0. And we know what is the generating function of Zn. So probability for Zn equals 0 is the generating function at value 0. And here we see that if we define Q as the limit of the sequence, and then if we compose F to both sides, this is just Fn plus 1, n plus 1 composition of F. So the right-hand side will again give us the limit Q. So here we can already see that this Q has to be a fixed point of F. So then, in order to calculate what is this extinction probability Q, we need to analyze where is the fixed points of this function F. So now we analyze this F. So what happens to this F? So for this generating function, we know that when S equals 0, it equals P0. So it's the probability that we have 0 child in one step. And we also know that when S equals 1, it equals 1. And it is strictly increasing and strictly convex. So probably the graph of this function will look like this. And we want to study where is the fixed point. So the fixed point would be the point that this is the graph of function and it's the intersection with y equals x straight line. So this is the graph of F and this is y equals x. And then we can see that here is a fixed point, because we always have f1 equals 1. And here is another possibility for the fixed point. Okay, suppose, so first, because we know that F is a strictly convex, this tells us F has at most 2 fixed points. Fixed points. And then we know that Q is the limit of Fn0. So we start from P0, and then we take what is Fp0. So first, this is F0, and F10 is Fp0, so it is here. And then we take another composition of this value here, and then this point is here. So from the graph, we can see that this is an increasing sequence. So this is an increasing sequence, and it's convergent to the smaller fixed point of the function. So Fn0 increases to the smallest. So first we know that since F is a strictly convex, there are at most 2 fixed points. And we already know that we have 1 at 1. And second, we know that this sequence Fn0 will increasingly converge to the smallest fixed point. And this smallest fixed point is our extinction probability. So there are at most 2. So if there is only 1, then we already say that Q equals 1. But if there are 2, then this Q is the smaller one. So combining these 2 observations, we can already see that this extinction Q is the smallest fixed point. Is the smallest fixed point of f. And then the next step is we need to decide when f has 2 fixed points and when it has only 1. Okay, so how many fixed points? So how many fixed points does f have? So the number is 1 or 2. And here we go back to the graph of this function. So now suppose we look at what happens to the derivative at 1. So now we want to look at the derivative of this function at 1. So suppose that this derivative is small, is less than 1. Then our curve will look like this. And here is p0, here is 1. So if the derivative at 1 is less than 1, then we will probably the graph of this function will look like this. And then there's no other fixed point except 1. And if the derivative at 1 is strictly greater than 1, then the graph of this function will look like this. And here is p0, here is 1. And in this case, we see that except 1, we have another fixed point. And this is the rough idea from the graph. And in fact, this idea can be made precise. So we have 2 cases. First case, the derivative of function f at 1 is less than 1. So suppose the derivative is less than 1, and our conclusion is there exists a unique fixed point. So there is only one fixed point at s equals 1. So why this is true? So now we know that this f is the derivative is strictly positive, and the second derivative is also strictly positive. So this implies that the derivative of s is also increasing. So this implies that the derivative of f is increasing. And we know that the derivative of f is less than 1 at 1. So this tells us the derivative of f is strictly less than 1 before x is smaller than 1. And now look at what's the difference between fx and x. So we define the difference as fx minus x as gx. So first we know that the derivative of x of g equals the derivative minus 1, and it is negative. So this g is decreasing. Since g is decreasing, we know that gx is always greater than g1. And when x equals 1, f1 equals 1, this equals 1, and this is 0. And in fact, here we can show it is strictly greater than 1, because here is strictly less than 0. So this tells us for x between 0 and 1, we have xx strictly greater than x. So there's no fixed points except s equals 1. So this proves that when the derivative of a function f at 1 is less than 1, so this is equivalent to the mean of the distribution. So if m is less than 1, we already know that there exists a unique fixed point, so q equals 1. This is the first case. And second case, the derivative of function at 1 is strictly greater than 1. So what happens to this case? So we know that the derivative here is strictly greater than 1. And of course, because this f is smooth, so it is usually strictly greater than 1 in a small neighborhood of 1. And this tells us for some x that is very close to 1, we have that fx is less than x. And however, we also know that when x equals 0, f0 is p0. And this is greater than 0. So for this function at 0, it is positive, and here it is negative. So there will be one unique solution that it equals 0. So this tells us there exists another fixed point. That is strictly less than 1. It is possible that this fixed point is at 0. So in this case, we know that if the derivative or the mean is strictly greater than 1, then this q equals this smaller fixed point, and it is strictly less than 1. So we have strictly positive chance to survive. Okay, so this is the proof of this theorem. Okay, so this theorem tells us our intuitive idea is correct. So if the mean is small, then the tree almost surely dies. And if the mean is strictly greater than 1, then we have strictly positive chance to survive. Okay. So now we have proved that for this Galton-Watson tree, in fact, there are 3 different cases. One is called supercritical. So supercritical means the mean is strictly greater than 1. And in this case, we know that we have strictly positive chance to survive. Or critical case. So critical case means m equals 1. And the subcritical case, m less than 1. So in fact, subcritical m strictly less than 1, critical m equals 1, and the supercritical is m strictly greater than 1. If we want to just answer the first question about the extinction probability, there's no difference for these two. So in the critical and the subcritical, the extinction probability is always 1. So almost surely the tree dies. But for a supercritical case, there's a positive chance to survive. But if you want to study what's the asymptotic of the probability for Zn equals 0, then these 2 cases will give you two different asymptotic behavior. So one will decay in polynomial way, in exponential way, and another one will decay in polynomial way. But today we won't discuss this problem. So we want to further ask another question that is strict to supercritical case. So now we restrict to supercritical case. And in supercritical case, we know that we have strictly positive chance to survive. And the next question is, if we know that we will survive, then how fast the tree grows? So given that we will survive, so how fast the tree grows? So how fast the Zn grows as a function in n? We know that the expectation of Zn is m to the power n. So a gases this Cn will increase as m to the power n. And we want to ask whether this intuitive idea is correct. So this introduces the next question. So whether do we have Zn increase like m to the power n? So to answer this question, we introduce another quantity, Wn. So Wn is Zn normalized by m to the power n. So first, we claim that this Wn is a martingale. Okay, a quick proof. So Wn plus 1 is the expectation of Zn plus 1 given Fn and normalized by this quantity. And we know that we just did the conditional expectation of this part. So we know that given Zn, the conditional probability of Zn plus 1 equals m times Zn. So this tells us the conditional expectation of Wn plus 1 equals Wn. So this tells us this Wn is a martingale. And the second observation is this is a non-negative martingale. So of course it is non-negative because Zn are positive integers. So since this Wn is a non-negative martingale, we have almost sure convergence. So we know that Wn converges to some limit almost surely. Okay, since this Wn converges to W infinity almost surely, then we know that this Zn, as n goes to infinity, will increase as Wn times m to the power n. So here we see that if W infinity is strictly positive, then this tells us Zn does increase as m to the power n. But if W infinity is 0, so this tells us Zn increase smaller than m to the power n. So in order to answer the second question, whether the population of the tree increase in this way, we have to derive W infinity is strictly positive or it equals 0. Okay, so this is the second question. And the answer to this question is called the Kasten-Stigm theorem. So this theorem says the expectation of W is 1 is equivalent to say that condition on the survival, W is strictly positive is 1. So as long as Y survive, then W is always strictly positive. And the criteria to check this, whether this is true, is a criteria on this random distribution mu. Okay, and these three conditions are if and only if, but we won't give the proof of the theorem. We will prove a weaker theorem. So a weaker version of the theorem. So the weaker version of the theorem says, suppose the random measure is a square integrable. Then we can answer the question. So the answer is, then we have that the expectation of W infinity equals 1. And we also know that so condition on non-extinction, the probability, it is almost surely that this limit is strictly positive. So given that we survive, and then we know that this Zn will increase as a power as in an exponential fast way of n. Okay, so why this is true? Before we prove the theorem, we'll prove this little lemma. So the lemma says the probability for the limit W infinity is 0 is either Q or 1. So in this lemma, we study what's the probability that the limit is 0. So now we will give, to prove this lemma, we will change our point of view to this random tree. So previously, we always given what happens to Zn and study what happens to the next generation. And now we change our point of view. So we see, so suppose now that this is the ancestor, and it has Z1 children. So there are Z1 children. And now we condition what now we ask what happens to the n+1 generation. And here we see that suppose we know how many particles we have in the first generation, then this is 3 subtree are just a 3 independent copy of random trees up to the generation n. So this tells us, in fact, Zn, suppose we know what, so given Z1, then it's Zn is the summation of subtree of Z1 number of subtree, and each one is an IID copy to the nth generation. Wait. So because we know that given how many particles do we have in the first generation, then what happens here are just a Z1 independent copy of what happens to the nth generation. Okay, and now we normalize both sides by the expectation. So what we have is Wn plus 1 equals 1 over m. Wjn. And here, in the right-hand side, Wj's are just the IID copy of Wn. And now, given Z1, we let n goes to infinity. So we have almost sure convergence of this Wn, and we also have almost sure convergence of this Wj to the right-hand side. So let n goes to infinity. We know that this one will converge us to W infinity. And for the right-hand side, it converges to something that is the summation of IID copies of W infinity. It's almost surely. Okay. So now let us look at the probability that W infinity equals 0. So P is the probability W infinity equals 0. And now we're given what happens to Z1. Given what happens to Z1, and we know that this W infinity is the summation of Z1 copies of itself. So, and all of them are independent of Z1. So in order for W infinity to equal 0, all of them equal 0. And there are Z1 of them. So it is P to the power Z1. And by the definition, this is just the generating function at P. So here we see that this probability P is a fixed point of this F. And from the proof of the previous theorem, we know that there are only 2 fixed points. One is Q and another is 1. So this probability is either Q or 1. Okay, so this is the proof of this lemma, and then we can prove the theorem. So the theorem says if we have finite second moment, then in fact we will prove that the martingale Wn will converge in L1. So theorem says if we have finite second moment, then proof. So in fact, when we have finite second moment, we will show that this Wn is a martingale that is bounded in L2. And suppose we prove that Wn is bounded in L2, then we know that Wn will converge in L2. And it also implies that Wn is Ui, so there is also convergence in L1. So suppose this is true, then we already know that since Wn converged to W infinity in L1, so the expectation of W infinity equals 1. And from this lemma, we know that the probability of W infinity equals 0 is either Q or 1. So if the expectation of this guy is 1, then this tells us the probability for it equals 0 has to be Q, because if it equals 1, then this W infinity equals 0 almost everywhere. Then the expectation is also should be 0. It can't be 1. So this tells us the probability for it is 0 is Q. And of course, this also says W infinity is strictly positive equals 1 minus Q. And we also know that the probability for non-extinction, so the probability for the tree to survive, is also 1 minus Q. And W infinity is strictly positive, means Zn can never be 0. So this is a subset of non-extinction, but they have the same probability. This implies the conditional probability given survival is 1. Okay, so here we see that after we prove this Wn martingale is a bounded martingale in L2, then we complete the proof of this theorem. So the only remaining thing is to check Wn is bounded in L2. And to this end, we have to calculate what's the expectation of Wn squared. So we see what is the relation between n plus 1 and 2n. So what is Wn plus 1? So we calculate what's Cn plus 1 squared. We know that given Zn plus 1 is just so given Zn plus 1 is the summation of IID random variables, and there are Zn of them. So we expand this square, so this gives us there are Zn diagonal terms. And that's Cn times Cn minus 1 terms outside diagonal. And for terms outside diagonal, we know that it is m squared. And here, this c square we denote it by sigma squared plus m squared. So this this sigma square is just a variance of this random variable. And by the assumption that we know this sigma square is finite. Okay, so here what we have is, this is sigma square plus m squared. So rearrange. We have Zn times sigma squared plus Zn squared times m squared. Okay, so we continue. So we know that, so the first term is just the sigma squared times the expectation of Zn. And the expectation of Zn is m to the power n. And then m squared times the expectation of Zn squared. So here what we have is, this is sigma squared m plus 2 times m2n expectation of Zn squared. So here we see that this term is exactly the expectation of Wn squared. And so here we have already seen the difference between n plus 1 and n. So we prove by induction that, so this tells us so this is the expectation of Wn squared. And here, since our m is strictly greater than 1, we know that for the right-hand side, as n goes to infinity, it is bounded by a universal constant. And this proves that this Wn is a martingale bounded in L2. And this completes the proof of this theorem. Okay, so we have a break and we resume at 20 past 10. Okay, so second part of today's lecture will about backward martingale. So before we talk about what is backward martingale, we will first prove 0-1 law. So of course you already know how to prove it. Just in today's lecture, I will give another proof by convergence of martingales. Okay, 0-1 law. So suppose Ci is an independent sequence, and then we define Gn is the information of the tail event. So as n goes to infinity, we see that this Gn is decreasing. So it's just the information of the tail events. We don't know what happens to from 1 to n minus 1, we only know the information for the future part. And this is a decreasing sequence of sigma algebra. And we define the limit to be at G infinity. So this is a small sigma algebra because it is the decreasing limit. And the conclusion is this tail event G infinity is trivial. And we say it is trivial. The meaning is for any event in this G infinity, the probability of this event is either 0 or 1. So this is say that it is trivial. So why this is true? So now we will give a new proof by convergence of Martingale. So we define Fn in the usual way we like. So it is the information up to n. And then we define a new random variable. It is the conditional expectation of A given Fn. Then by theorem for convergence of UI martingale, we know that this Xn is a UI martingale. And since it is UI, we know that we have convergence almost surely and also convergence in L1. So on the one hand, since this is a UI martingale, we have almost sure and convergence in L1. And then let us check what is x infinity. So xn is the conditional expectation of A given Fn. And as n goes to infinity, this Fn will increase to all the information we have. So of course, this all information f infinity is already give us the information of A. So then the conditional expectation will just become the function itself. So this tells us x infinity equals this function itself. It is the indicator function of A. Okay. On the other hand, let us check what is this xn. So xn is the conditional expectation of 1a given Fn. And here we know that A is in G infinity. So G infinity is contained in Gn minus 1, Gn plus 1. And Gn plus 1 is all the information of random variables after time n plus 1. So this Gn plus 1 is independent of Fn. So Fn is the information from 1 to n, and the Gn plus 1 is the information after n. So they are independent sigma algebra. And since this Fn is independent of this event A, we know that this conditional expectation is still the probability of this A. So combining these two parts, we know that the probability of A converges to A, to indicator of A, almost surely and in L1. So now this tells us this constant probability of A equals the indicator function of A. So this probability is either 0 or 1. This is a new proof for 0-1 law. Is there any question? Okay, then we can talk about what is backward martingale. So for the backward martingale, we consider a decreasing sequence of filtration. So when we define forward martingale, first we will give an increasing sequence of filtrations, and we say that this. So just to recall, what is forward martingale? So for forward martingale, we have a sequence of filtrations that is increasing. And we say that xn is a martingale with respect to this filtration. For each n, xn is Fn measurable. And on the other hand, we also have that the conditional expectation of xn plus 1 given Fn equals xn. So this is a forward martingale. And today we introduce backward martingale. So for backward martingale, first, the sequence of filtration we are considering is a decreasing sequence. But in order to keep the same notations as martingales, we will index this sequence by minus integers, so that this is a still increasing sequence in the index. So now we have a sequence of filtrations indexed by negative integer. And we say Xn is a martingale. It's a backward martingale. So it is also indexed by negative integers. So it is a backward martingale if first Xn is Gn measurable. Second, the conditional expectation of Xn plus 1 given Gn equals Xn. So here we see that formally these two conditions are the same, but now all the indexes is indexed by negative integers. Okay, this is a backward martingale. So from definition here, we see that by Tower property, we always have Xn equals the conditional expectation of X0 given Gn. But here n is a negative integer. And since this is true, we already know that for any backward martingale, it is already Ui. It is already uniformly integrable. So now, in fact, we can repeat all the proof for forward martingale to show that if Xn is a backward martingale and X0 is an LP, then we have convergence in LP, and also the almost sure convergence. So we can repeat exactly the same proof for all the other cases. We have Xn converges to x minus infinity. Almost surely, and in LP. So here, there's no difference between P equals 1 or strictly greater than 1, because this martingale is already uniformly integrable. So there's no difference between P equals 1 or P strictly greater than 1. Okay, so this is the backward martingale, and all the conclusions for, yes?
Sorry.
Okay, and for all the convergence theorem for backward martingale, as for forward martingale is also true for backward martingale. And I summarized here, and you can check after the lectures item by item, so the proof works exactly here. And then by the backward martingale, the convergence for the backward martingale, we can give a new proof for strong law of large numbers. Strong law of large numbers. Okay, so for the strong law of large numbers, it says that we have an independent sequence, IID sequence, and they have finite mean. And we say this mean is mu. And the strong law of large numbers says Sn is the summation of 1 to n normalized by n. Summation of 1 to n. And strong law of large numbers says Sn normalized by n will converge almost surely to mu. And here, by the language of backward martingale, in fact, we can prove there is also convergence in L1 for free. So usually for strong law of large numbers, we only prove the almost sure convergence. And now we have convergence in L1 for free by the language of backward martingale. Okay, a new proof for strong law of larger numbers. So now we define a sequence of sigma algebras indexed by minus integer and this is the information of all Sn after n. And we index by minus n here, so this Gn, we can already check that this satisfies the same relation here we introduced in the definition of backward martingale. And then we define Xn equals Sn over n. And the first claim is this sequence Xn is the backward martingale. Okay, so in order to check this Xn is a backward martingale, the only thing we need to check is we have this relation. So after this is proved, then we know that this Xn is a backward martingale. So now let us check what is the conditional expectation in the left-hand side. So you change the language to here. So it is equivalent to say that we need to calculate the conditional expectation of Sn minus 1 given what happens to So it is equivalent to check that the conditional expectation given for what happens after n, we predict what happens to n minus 1. It equals Sn over n. Okay, so let us check what's the left-hand side. For the left-hand side, we calculate the conditional expectation. And here, this is the sigma algebra we know. And here we know that this Sn plus 1 is Sn plus Cn plus 1. And here, this Cn plus 1 is independent of Sn. And it is also independent of Sn minus 1. So there's so given this information, it doesn't help us to calculate the conditional expectation. So the left-hand side equals the conditional expectation given information of Sn. Because all the information of this future term doesn't help us to calculate the conditional expectation. Okay. So now, what's the relation between Sn minus 1 and Sn? So Sn is Sn minus 1 plus Cn. So Sn minus 1 is Sn minus Cn. And given the information of Sn, of course, this guy will take out. So what we have is and from the first, the calculation in the first lecture of our martingales, so there we first introduced what is the conditional expectation. And this is the only example we calculate there. And this guy equals Sn over n. And the idea of the proof here is because if we change this n to some integer k that is less than n, then all of them should be the same. Because all of them are ID, given the information of their summation, they should for different k, they should be the same. So everyone equals Sn over n. So here, from the first lecture of martingales, we know that the conditional expectation of Cn given Sn is Sn over n. And this is exactly Sn over n, and this is the right-hand side as desired. Okay, so here we just check that the sequence Xn is a backward martingale with respect to filtration Gn. So by the convergence theorem for backward martingale, we know that this Xn will converge to x minus infinity almost surely in L1. So this tells us Sn over n will converge to something almost surely in L1. And now we only need to check what is this limit, y. So y is the almost sure limit of Sn over n. And we can also see that for any k, so for any k, we also know that this y is also the almost sure limit of the summation from k plus 1 to k plus n and normalized by n, almost surely. So this is from Sn over n converge almost surely to y. We know that we have almost sure convergence in this for any summation from k plus 1 to k plus n. So just to stress that this is not just to have the same law, they are exactly the same thing. So of course, if we just look at the right-hand side here, this guy has the same law as this guy. But because we have the almost sure convergence here, we have the almost surely they are the same thing. So they're not just only have the same law, they are exactly the same thing. Okay, so y is also the limit of the summation here. And here in the right-hand side, we see that it has nothing to do with what happens before time k. So this limit y has nothing to do with what happens up to time k. And as k goes to infinity, we know that this y has nothing to do with all the finite information. So y is contained in tail event g minus infinity if I use the same notation there. Maybe I should change it to another notation. So from the observation here, we know that this y is measurable with respect to jk. And this is true for any k, so this y is measurable with respect to g infinity. This is tail sigma algebra. And by 0-1 law, we know that this g infinity is trivial. And since it is trivial, we know that this y equals c, c is some fixed number. So for any fixed number c, y equals c is an event in g infinity. And g infinity is trivial, means for any c, this probability is either 0 or 1. And of course, there can't be two different c such that this event has probability 1. So there exists a unique c such that this probability equals 1, and for all other c's, the probability is 0. So this tells us, in fact, this y is almost surely a constant. So y equals c almost surely for some constant. And from the conclusion there, we know that we also have Sn normalized by n goes to y in L1. Since the convergence in L1, we know that the expectation of y equals mu. And we also know that y is just a constant. So this tells us this constant has to be mu. Okay, so this completes the proof. So now we have proved that Sn normalized by n converge to mu almost surely any in L1. Okay, so this is a new proof for strong law of large numbers. And I will stop here. And in the next lecture, we will talk about a new proof for law of iterated logarithm and a new proof for the Random-Nikodym theorem. So I stop here.